to the session on deep learning algorithms. We will start with a long oral session followed by a series of short talks. Our first talk is going to be about something that people find really hard to do, and that is admitting that they don't know. So the title of the first talk is a selective net, a deep neural network with an integrated reject option. And the talk will be given by Jonathan Geifman, and the other author is Ran El-Yaniv.
Hello. So we consider the problem of selective prediction, which also known as prediction with reject option. Our focus is on applications of deep neural networks. This is a joint work with Ran El-Yaniv. Our motivation is based on the need to deploy highly reliable deep learning models for mission-critical tasks. For example, we want our autonomous cars to be able to detect uncertain situations, such as in these images, and to act correspondingly with avoiding maneuver. Reject option is strongly related to uncertainty estimation problem. Let's first map the landscape of uncertainty estimation and its application. Uncertainty estimation is the problem of qualifying any prediction with a score that reflects its probability of being correct. Below, we can see some of the applications of uncertainty estimation starting from selective prediction, which is the application that we are going to talk about today. Uncertainty estimation is also strongly related to a common strategy used in active learning, where points to be labeled are selected based on their uncertainty estimate. This strategy is called uncertainty sampling. Probability calibration is an application where uncertainty is calibrated to probability using methods such as isotonic regression and plot scaling. Our work can be motivated by the following simple example. The teacher announced that the final exam in the machine learning course will cover 10 topics, and the exam will include 10 questions, 1 question in each topic. But students will be able to choose 5 questions to answer among the 10. Bob decides to study all 10 topics, while Alice decides to study only the 5 easiest chapters. Let me now ask you a question. Which strategy is better? Alice's strategy, or maybe Bob's strategy? Maybe we can think about something in the middle between Alice and Bob. Let's consider Alice's strategy. How can you implement this strategy? How can she tell which 5 topics are easier before studying all the 10 topics? In this context, Bob's strategy corresponds to a standard selective classifier, which can abstain from prediction based on an uncertainty estimates at test time. In contrast, Alice corresponds to a refined selective prediction strategy that utilizes the required test time coverage during training. Recall some concepts from supervised statistical learning. Based on a training set that is sampled from an unknown distribution P, our goal is to minimize the true risk. This is usually done by minimizing the empirical risk over the training set while adding some regularization, which is often sufficient for obtaining good generalization. A selective classifier is a pair FG, where F is a standard classifier and G is a selection function. When G equals 1, the selective classifier will return the value of Fx. However, when Gx is 0, the selective classifier will return I don't know. The coverage is defined as the expectation of Gx over P. The empirical coverage can be defined correspondingly based on any IID unlabeled set. The selective risk is defined as the standard risk projected over the covered domain. Note that we use the term selective classifier and selective classification, but all our definitions and results can be extended to regression as well. It is common to quantify selective classification performance by the risk coverage trade-off. The risk coverage trade-off quantifies how coverage is traded for the risk reduction. We depict it over a 2-dimensional plane where the x-axis is the coverage, whose range is 0 to 1, and the y-axis is the risk. Starting from full coverage, which is 1, where we get the risk of a standard classifier without rejection. We expect a meaningful selective classifier to reduce the risk while coverage is compromised. Each point on this curve represents a selective classifier optimized for a different coverage rate. The performance of selective prediction strategy is measured via a family of selective classifiers optimized for various coverage rates. Since we measure risk, in this curve, lower is better. To facilitate a discussion of the related work, we define the confidence rate function. A confidence rate function, denoted as kappa, assigns an ordinal confidence score for any instance x. An ideal confidence rate function should satisfy the following condition. Consider 2 points, x1 and x2. We expect the ideal kappa of x1 to be higher than that of x2 if and only if the probability for error in x2 is higher than x1. By ignoring calibration requirements and only considering relative values, we simplify the problem of uncertainty estimation. The simplest and well-known kappa function is the softmax response. This means that we simply take the maximal value of the softmax output to be the confidence score. Softmax response corresponds to the distance from decision boundary that was widely used in many classifiers and notable support vector machines. There are several variants of this technique, including taking the entropy of the softmax vector or taking some other statistics, such as the difference from the top to the second value of the softmax output. Note that the softmax values are definitely not calibrated probabilities, even though they are positive and sum to 1. Clearly, maximum softmax response is a valid confidence score for classification. However, it is not suitable for regression tasks. Gal and Gaharamani proposed the Monte Carlo dropout, which is acronymed MC dropout, and they motivate it on Bayesian grounds. MC dropout is confidence rate function computed by running a number of feed-forward passes where dropout is applied on some layers in the network. A typical number of forward runs is 100. The intuition is that each dropout pass corresponds to sampling one network from a distribution over the networks. Statistics gathered from these 100 iterations over the sample network can be used as a confidence rate function. For example, the variance of this 100 iteration can reflect uncertainty. In a recent NeurIPS paper, we proposed a simple and effective selective classification approach that is based on threshold over kappa. The G function is defined as a threshold theta over kappa. The values of theta is trained over an independent validation set. The NeurIPS paper I mentioned also proposed a baseline for comparing selective classifiers or uncertainty method in the context of selective classifiers. It was shown that the softmax response is a very good baseline that is not easy to beat. The MC dropout could not beat softmax response in all of our experiments, and somewhat surprisingly was even sometimes inferior. Here we see an example of ImageNet with ResNet 50, where the top 1 and top 5 errors are depicted in the graph. Clearly, in this case, you will prefer the softmax response over the MC dropout. I will soon show how to beat softmax response based on our approach called SelectiveNet. Based on another recent work, we can see that the softmax response is not optimal. An interesting question is what makes softmax response non-optimal. In our context of SGD optimization of deep neural models, there is a partial answer which is based on the following observation, for which I will only describe in high level. Each of the two graphs show the quality of the softmax response as an uncertainty estimator along the training process. Smaller values correspond to good estimation. The x-axis corresponds to the epochs during training. The green graph is projection of this softmax quality over the easy points, which are taken in hindsight to be the 50% most confident points in the test set. The red graph is similarly obtained by the bottom 50% points. For them, our model is the least confident. We can call them the hard points. Notice that the quality of softmax response as another certainty estimator is good for the hard point, but for the easy points, it's getting better and better along training and then degrades. If we assume that we don't need to classify all the domain, but only a portion of the domain, like 70%, we can reduce this effect, this degradation effect, in the training of the softmax response output. We now describe the selective net architecture. The main body block is based on any feature generation network that may be based on a known architecture such as ResNet or DenseNet. We connect to the main body block two prediction blocks. The first is the prediction block that should solve the learning problem at hand. For example, if we are interested in classifying Cypher 10 images, this could be several neural networks layer ending by a 10-unit softmax layer. If the task is to predict house prices, we can end up with one linear neuron. The point here is that selective net can solve both classification and regression. This head is the prediction F that was formulated in selective classification approach. The second output of the network is the head G. It ends up with one sigmoid neuron that its values are in the range 0 to 1. This will be the selection function that we formulated earlier. The optimization of selective net is inspired by interior point method and optimization with barrier functions, where optimization is applied within the feasible set. The optimization objective is minimizing the selective risk with an inequality constraint over the coverage. The value C is the minimal coverage allowed for the selective classifier and is defined by the user. We use a quadratic barrier function to penalize the objective to be in the feasible set and optimize the following objective, that is the empirical selective risk with a penalty constraint over the coverage. At this point, where we explain the selective net architecture, we go back to Bob and Ali's story from the beginning. This story motivated the problem faced by SelectiveNet. Recall the story where Alice decided to study only 5 chapters, and Bob decided to study all the 10 chapters. Even if we agree that Alice's strategy is better, it is not clear how she will be able to decide on the easiest 5 chapters without studying all the 10. It turns out that the same problem prevents SelectiveNet from reaching non-trivial results. In our context, how can G learn which part to cover before an F is converged? This is kind of a chicken and egg problem. If we are going to discard part of the domain using some early G, which is not fully trained, we are likely to discard word instances and reach a trivial selective classifier with bad results. In order to G to learn something that is relevant, the network itself should know something about the entire domain. But if the network does not specialize on some part at all, it will now give powerful results. It turns out that a rather simple idea can solve the chicken and egg problem. We introduce an auxiliary head, which is simply another prediction head, depicted in gray here. This head forced the network, the main body block, to learn features extraction that is based on the entire domain. The task is to learn the original prediction task, classification or rejection, but without the selective risk. In other words, in contrast to the prediction head that is optimized with selective loss, the auxiliary head is optimized with the standard loss for the original learning task. The auxiliary loss causes the main body block to learn richer features that are based on the entire domain and boost the convergence of the prediction and selection head. In the case of Alice, this learning provides sufficient general knowledge to the entire domain that Alice can choose which 5 chapters to study for the exam. Technically, the auxiliary loss is added to the selective loss by a convex combination with a hyperparameter alpha that has been set for 1/2 in all of our experiments. Our experimental results show consistent and significant improvement over the softmax response. for classification over several datasets. Here, we see the results for the Cypher10 and cats versus dog datasets. SelectiveNet appears in blue, and softmax response appear in red. When zooming in, we see a 40% selective risk reduction for cats versus dogs in 80% coverage. We also show results for regression over the concrete compressive strengths dataset. We compare the result with rejection baseline obtained with MC dropout. Here again, we outperform the baseline with a large margin. Note also that SelectiveNet is much more efficient for inference compared to MC dropout. Here we took the Cypher10 embedding layer of SelectiveNet with 80% coverage and visualized it using t-SNE. We show in bold the rejected instances, the 20%, and we faded the 80% cover domain. We can see that SelectiveNet does not learn how to classify the rejected instances and mix all of them in a don't know region in the middle of the domain. In contrast, in the threshold method, we see that the rejected instances are embedded close to their classes. It shows that SelectiveNet does not invest representational capacity in order to classify instances that are going to be rejected at test time. This might be one of the reasons for the performance improvement that we showed earlier. In conclusion, we show state-of-the-art result for deep selective prediction compared to softmax response and MC dropout. We showed it over several datasets. In contrast to prior work, SelectiveNet does not require additional validation set for calibration. We also show a significant improvement for regression, where in this setting, our method is also much more efficient compared to MC dropout. For more details, visit us at poster number 1 tonight at 6:30. Thank you. I will be happy to answer any questions.
We do have time for a few questions. There are microphones in the aisles. In the meantime, the speakers of the short orals, please come forward and sit in the front. Any questions?
Yeah, quick question. Thank you for the talk. Over the course of training, do the I don't know examples move to the knows, or do they stay I don't knows from the beginning? In other words, does the net get better at distinguishing those?
Because of the optimization method, these I don't know instances are building along the training. We begin with almost none I don't know instances, and we get more and more while we train the network. This is because the auxiliary output that inject gradients to the main body block.
Thank you.
Yeah. The question was how SelectiveNet responds to instances that have not seen like out-of-distribution examples. We consider out-of-distribution example as different task. We mainly focused in the IID setting. Out-of-distribution, in our view, need different machinery. That some of the papers, there's existing literature that proposed some other methods for out-of-distribution. Here we focused on IID.
Thank you, Jonathan.
Thank you.
So our next talk is by Alex Lam. It's going to be about manifold mix-up, getting better representation by interpolating hidden states.
What do I do with that?
We can just.
Okay.
Whatever.
Hello, I'm Alex Lamb. Today I'll be presenting Manifold Mixup, a new algorithm with good practical results, which is also backed up by some rigorous theory. Now, first I want to draw your attention to some troubling properties with today's deep neural networks. And I want you to first just draw your attention to the column on the left, where we have a simple binary classification task with these spirals. The two classes are these blue and red dots. And the first thing I want to draw so another thing is on the bottom, we have a 2D bottleneck hidden state being visualized. And one thing you can see is that even though all of the different confidence levels are visualized, you almost can't see them in this figure because the networks are almost always confident at every point or in the data space and also in the hidden space. And there's some other troubling properties here. One is that in the hidden space, the states of real data points are very spread out, and there's not a lot of compression of the information. And another troubling property is that the decision boundary comes very close to the real data points. So these are the issues I've discussed. And we're going to present a simple algorithm called manifold mixup, which helps to address these issues. So the way manifold mixup works is on every training update, you pick a random layer, and you, at this layer, you're going to mix between the hidden states of different random examples. And when you do this mixing, you're going to pick a random rate lambda to mix between them. So you can use different distributions for this. You can use a uniform distribution. You can use a beta distribution. That detail's not that important. So what is important, though, is what you're going to do is you're going to mix between them. For example, you're going to take 80% A and 20% B. You'll do the linear interpolation, and then you pass that through the rest of the network. And then you're going to train it to have the same linear interpolation of the targets. So if you took 80% A, 20% B in the hidden states, you're going to train the target for that to be 80% A and 20% B. And one of the cool things about that is that means that these interpolated states, the network is trained to be much less confident. This achieves some great results. CFAR, SVHN, Tiny ImageNet. Others have used this and gotten good results on ImageNet. One of the most striking things is that the test likelihood is often dramatically better. It's sometimes like cut in half. And we think what that means is that when the model is making mistakes on the test set, it's less confident in those mistakes that it's making. And I'll also draw attention to the fact that other labs have used manifold mixup already, and they've achieved great results across a variety of tasks. Now, let me return to the same 2D spiral task that we looked at the first slide. In the bottom right, you can see what it looks like in the data space, and you can see that there's a large region of low confidence. And if you look at the hidden space in the middle, you can also see that there's a large region of low confidence. And you can also see that the hidden representations of real examples have much better concentration. And we also performed some somewhat more sophisticated experiments to confirm that this also happens in higher dimensional hidden spaces, but it's very easy to see when you look at a two-dimensional hidden space. And to make this more concrete, we also produced some theory showing that there's a relationship between the number of classes and the dimensionality of the hidden states. And kind of the key takeaway from this is that when you use manifold mix-up, the hidden representations from real examples go onto a lower dimensional linear subspace. So the vast majority of your hidden space will correspond to low confidence predictions. To kind of wrap things up, manifold mix-up can help a lot on any classification task, especially where you're concerned with likelihood. It can also help where you have small amounts of labeled data. And I think there's also a lot of exciting work left to do on the theoretical end. We make a lot of very precise assumptions that could be relaxed. It would be cool to look at this in RNNs. I think another thing would be going deeper in the property of the learned representations. For example, there's some exciting work on the spectral properties of linear neural networks. So I think going in that direction could also be exciting. Just to wrap things up, if you have any more questions or anything else you want to discuss, myself and my colleagues would be happy to do so. So thank you for your time.
Our next talk is about processing megapixel images with deep attention sampling models. And the talk is given by Angelos Katharopoulos.
Hello, I'm Angelos, and I will present work that we did with my PhD advisor, François Fleuret, on processing large images with deep attention sampling models. Traditional neural network pipelines do not handle directly large images because of the memory and computational constraints. And the two approaches to overcome this limitation is cropping and downsampling the images to a more manageable resolution, or dividing the images into patches and processing them separately. However, the first approach might lead to loss of information that is crucial for solving a task, and the second requires access to per patch labels, which are really difficult to come by. Instead, we propose to use a low-resolution view of the image to predict an attention distribution from which we sample interesting regions and process only a fraction of the image in high resolution. We also derive gradients through this sampling and train our model end-to-end, which means that we have a model whose computational requirements are decoupled from the input resolution. In detail, we consider attention to be basically the weighted sum of a set of features weighed by the corresponding attention weight. And this can be seen as the expectation of the features under the attention distribution. In order to save computation, we don't want to compute all the features, so instead we approximate this expectation using Monte Carlo, which mainly means we sample locations from the attention distribution and compute the features only at those locations. Here we have two theoretical results. We show that sampling from this attention distribution is optimal. It is the best distribution we can sample from when the norm of the features is constant for all locations. And also we derive unbiased gradient estimators for both the parameters of our attention and feature function, which allows us to train our model end-to-end. The resulting pipeline is as follows. Given a large image X, we downsample it and pass it to the attention network that predicts the attention distribution. And then we sample locations from this attention distribution and extract patches from the high-resolution image in those locations that are then given to the feature network, and the features predicted are averaged and passed to the rest of the model to predict the output. For a brief qualitative evaluation of our attention sampling, we compare with a state-of-the-art attention model that computes the attention in the full high-resolution image, and we observe that both models attend to the same correct positions in the image, albeit with a bit more noise from the attention sampling perspective. This behavior is also observed in other real-world cases where the regions of interest are a lot fewer, as is in the case here where we have to predict the speed limit from a given image. regarding the quantitative evaluation, we observe that our attention sampling achieves the same test error as the full attention model, using only an order of magnitude less memory and an order of magnitude less walk log time. Thank you very much. We also have published code, and you can come talk to us at poster number 3 if you want to discuss. Thank you.
Our next talk is TAPNet, neural network augmented with task adaptive projection for future learning. And the talk is given by Sang-Wan Yoon.
Good morning, everyone. My name is Sang-Wan Yoon from KAIST. Today, I will introduce our future learning algorithm, task adaptive projection network that we call TAPNet. Future learning is to handle previously unseen classification tasks or episodes using only a few examples. To tackle the problem, the episodic training is used. Each time, a brand new task is presented to the model, and over time, the model learns to handle previously unseen classification tasks. Built upon the episodic training, our TAPNet employs a unique task conditioning method. TAPNet consists of 3 key elements: feature extractor, runner reference vectors, and task adaptive projection space M. The feature extractor and runner reference vectors are trained across episodes, but the projection space M is computed again for every episode as a form of task-dependent conditioning. First, support samples are processed by the feature extractor, and per-class averages are obtained. Based on the per-class averages and reference vectors, TAPNet computes an alternative classification space such that the averages and references match well in that space. Then we linearly project the embedded queries to that space and classify them with a distance metric to the projected reference vectors. For every episode, loss from the metric-based learning is used to update the feature extractor and runner reference vectors. The essence of our TAPNet is that the explicit task-dependent conditioning is employed by finding the task-adaptive projection space, and classification is done in that space. Also, we want to note that the projection space is computed directly from non-learning-based linear processing, simply by finding the space where the per-class averages and matching reference vectors pretty much align. Let's focus on the way to construct the projection space M. We first find the error vectors between the per-class averages and matching reference vectors. Our goal is to find the projection space where the error vectors are zero-forced. In other words, the per-class averages and matching reference vectors are closely aligned when they are projected to that space. A simple but optimal way to find the space is taking null space of the error vectors. For every episode, we compute the projection space with the same manner. Then classification space provides an effective task-dependent conditioning. For classification, the reference vectors and embedded queries are projected to that space. Then projected queries are classified into the nearest projected reference. You can actually see that the projection space gives better separation among classes than the original embedding space. This is a result of running omni-glit. Here we have trajectories of the reference vectors that are trained across episodes. You can see that the classification references grow apart as training goes on. Results confirm that our TAPNet shows excellent generalization performance. For various future learning classification tasks, our TAPNet achieves best accuracies. We believe TAPNet somehow gains good inductive bias and task adaptability. I hope you to come to our poster session for seeing further results and enjoying constructive discussions. Thank you.
Our next talk is about online meta-learning and is given by Chelsea Finn.
Arvind and I will be presenting our work on online meta-learning, which is joint work with Sham Kakade and Sergey Levin. Deep neural networks work very well when you have very large data sets. However, in many practical situations, we may want to learn tasks with only a few data points. Meta-learning accomplishes this by explicitly optimizing for efficient learning. These algorithms learn how to learn across a batch of tasks, such that when you see a new task, these algorithms can very efficiently learn that task. However, in many realistic real-world situations, our agents may not be given a batch of tasks right off the bat. Instead, they may be given tasks in sequence as they experience the world one at a time. Hence, a much more realistic embodiment of the meta-learning problem is one where tasks are presented in an online streaming fashion. At the beginning, agents learn slowly, akin to learning from scratch. However, as they learn more and more tasks, they simultaneously become faster at learning those tasks. How might we go about trying to formalize this problem statement? Well, one avenue for providing some inspiration is the problem of online learning. This problem statement evaluates an agent's ability to perform a sequence of tasks. However, it evaluates the ability of the agent to perform a task in zero shot, which may not be possible in a variety of situations. Hence, in this work, we propose the problem statement of online meta-learning, where the goal is for an agent to efficiently learn a sequence of tasks over time. And in particular, over time, we want the agent to be able to learn tasks more and more efficiently and more proficiently over time. In this work, we formalize this problem statement and develop methods for solving it, which Arvind will describe next.
So the online meta-learning setting comprises of the learning agent and the world, which in general could be non-stationary or even adversarial. The learning progresses in rounds, where in each round, the world first picks a loss function, and simultaneously, the agent also chooses a model parameter s by theta. Subsequently, the agent uses an update procedure to adapt its model to perform better at the task. An example of such an adaptation procedure would be a gradient descent using an approximate version of the loss function denoted by L hat. This approximate loss function can be based on just a few labeled examples in the case of few-shot supervised learning, or just a few trials of the task in the case of few-shot RL. Finally, the agent suffers the loss corresponding to the adapted model. Note that access to this approximate loss function and adaptation using its gradients is what distinguishes our online meta-learning setting from the conventional online learning paradigm. The goal in online meta-learning is to design algorithms whose regret grows as slowly as possible. The regret is defined as the difference in cumulative loss incurred by our algorithm when compared with the best possible algorithm in hindsight. The algorithm that we develop and study for this setting is follow the meta leader, which essentially performs meta learning on the previous tasks or loss functions. And this can be implemented with MAMO. We show that under fairly standard regularity conditions, which include second order smoothness and strong convexity, the regret of the FTML algorithm grows only logarithmically over rounds. What this means is that the average regret, which is the regret over t, quickly goes to 0 as t grows to infinity. And thus, even though we are learning in a sequential and non-stationary setting, we can very quickly be competitive with the best meta learner in hindsight. Chelsea will now present some experiments.
We develop a practical instantiation of our approach based on the MAML algorithm, and we experiment with a number of sequences of tasks. These sequences of tasks are based on transformations of the MNIST dataset, 3D object pose prediction as illustrated on the right, as well as C4100 classification. We evaluate both the learner's ability to learn efficiently and learn proficiently as it sees each new task. And in comparison to multiple strong online learning comparisons, we find that our approach significantly outperforms all approaches, both in terms of efficiency and in terms of proficiency, and critically is able to learn each new task with faster and faster and with greater and greater proficiency over time. And it even approaches the few-shot learning regime towards the end of online meta-learning. The takeaways of our work are that we introduced the online meta-learning problem formulation and showed that meta-learning is effective in non-stationary settings. And further, we showed that we can achieve similar guarantees to online learning, but superior empirical performance. And so to take away something from this work, we think that meta-learning is a critical component of online and lifelong meta-learning. And for more information, we'd love to see you at poster number 5. Thank you.
So our next talk is about training neural networks with local error signals, and the talk is going to be given by Lars Edens.
All right, so training neural networks with local error signals. This is joint work by Arild Nøkland and myself, Lars. So usually when we train neural networks, we use global backpropagation. We have a loss function at the end, and we minimize that by backpropagating the error through the weight layers. This obviously works really well, but there's perhaps some reasons why we might be motivated to find other ways of doing this. So, for example, it's hard to see how the brain could be doing this. There's all sorts of problems there where, for example, we keep the activations in memory after the forward pass, waiting for the backward pass. It's hard to see how the brain could be doing that. We use the transpose of the weights in the backward pass. It's hard to see how the brain could do that. And there's all sorts of interesting work that's been done trying to come up with biologically plausible explanations for how a brain could implement this. And so the approach we've taken here is to see how well can we do if we just sidestep the whole problem and train each layer with local error signals. So we don't propagate the error backwards through the layers. So if you do this, you can update the weights in the forward pass. And that has a lot of practical benefits as well. So because you don't need to keep the activations around in memory, you can just discard them when you're done with them. And that allows you to, if you're doing single GPU training, you can train bigger models or bigger batch sizes. If you're doing multi-GPU training, you can just send each layer to its own GPU and have each GPU be processing different batches of data at the same time. So that could speed things up a bit. So the single sentence takeaway from this is that it works pretty well. So in this table, the column to the right has the test error results on CFAR10 on the method we're proposing. We'll get back to the results later. So the approach we take here is we train a VGG-like network, which is a tree-by-tree convolutions, max pooling, rectifiers. There's a couple of fully connected layers at the end. And we also use batch norm. What we don't do is we don't propagate the error backwards through the weight layers. We just train each layer on its own. And that's done by connecting the layer to two subnetworks. Each subnetwork ends in a different loss function. One is the standard cross-entropy loss, and the other is the similarity matching loss, which I'll explain shortly. And before these losses, there's a single weight layer where we update the weights during training, but we don't use these weights during inference. You just find that having this extra layer there helps learn better representations. So this subnetwork we use for training can just be discarded during inference, and then you use it like a normal neural network. And one thing to say here is that some layer-wise methods, they train the first layer to convergence and then add the next layer, train that to convergence and so on. That's not what we do. We just train every layer all at once. So this similarity matching loss is basically the new part here. It's relatively simple to explain. So it's a squared error loss between two matrices. These matrices hold the pairwise similarities between the things in the batch. So one is the pairwise similarities for the activation vectors, and one is this pairwise similarity for the labels. So If you imagine you take the labels in a batch and you one-hot encode them, and then you take dot products between all pairs, you're going to get the matrix that has ones where the labels are the same and zeros where the labels are different, right? And this is going to be the target for our regression. And the other matrix holds, like if you take dot products between all pairs of activation vectors, you're going to get high numbers where they are similar and small numbers where they are dissimilar. So by regressing that matrix towards the labeled similarities, what you're saying is we want similar representations for things that have the same class and dissimilar representations otherwise. So there's a little bit more to it than just a dot product. We also normalized by length, so that gives us cosine similarity. We zero-center the vector, so it's like a correlation between two vectors. The gist of it is that it's the pairwise similarities between everything in the batch. And so some results, these are results on the like MNIST scale data sets. So there's a lot of data in these tables. So the 3 columns to the right have the results we get with the local learning. And the column to the left named globe, that's the results with global backprop. So the usual optimization method. So the pred column, that's where we use only the cross-entropy loss in a local learning setting. The sim column is where we use this similarity matching loss alone. And the pred sim column is when we use both. Yeah, so moving on to results for CFAR 10, CFAR 100. The column layouts are the same here. So in these tables, there's a few things that are interesting to compare. One is comparing these local losses alone versus combining them. So generally, we find that when we combine them, which is in the pred sim column here, we get lower test errors than using them on their own. And we always find that we get lower training error. So we'll get back to that later. Another comparison you might make is the results with local learning versus the results with global backprop. And for these architectures we're using, we find that these two are competitive. So that's going to be limited to these particular architectures, because these are architectures that have been chosen because they work well with local learning. So if you have a 50-layer RESTnet, backprop can optimize it, and local learning can't. We find that adding more layers beyond 11, accuracy tapers off. But at least for these particular architectures, and the data sets we've run on, we find that local learning and backprop are competitive. And also, you might compare the test results here with like the state of the art, and we find that, well, it gets surprisingly close, at least in my view. So here are some results on STL10 and SVHN. I should explain, the STL10 dataset was made for semi-supervised learning, so it has 5,000 labeled examples and a bunch of unlabeled data. So here we only use the labeled data, and we discard the unlabeled data. And there's not too many papers that have published results in this setting, but at the time of writing, this was the best published result we could find on this setting. And what seems to be, so here you have very few examples that are labeled, and the images are relatively big. They're 96 by 96 pixels. So this is kind of the data set where you might expect overfitting. And that seems to be what's happening with when you optimize this with normal backprop, is that you get overfitting. So this kind of suggests that part of why this works might be that it's a good regularizer. So if you dig into the training errors, we can sort of try to tease apart what comes from optimization and what comes from regularization. So generally what we always find is that backprop gets the fastest drop in training error, and it gets as lower than the other methods, which is not too surprising since it has the true gradient to optimize with. But local learning is competitive, at least for these architectures, in terms of test error. So it seems to be the case that local learning is a good regularizer. But that's not the whole story. So looking at the training error for the two local losses alone versus combining them, we in every single case find that when they're combined, we get a lower training error. So combining these help with optimization. And it helps with optimization in a global sense, right? Because we're measuring the classification error at the last, so classification error on the training set at the last layer. And these losses only know about their own single layer. But still, there seems to be an effect where it helps optimization in a global sense. So another thing you might do is to add this sim loss to each layer, but optimize the whole thing using global backprop. When you do that, we find that that works as a regularizer. It gives you, in some cases, better test errors than either local learning or plain backprop on its own. So part of the motivation for this is to take a step towards biological plausibility. There's still a lot of things that aren't biologically plausible. We use convolutions, we use negative numbers, and we ignore spiking. But it seems like a step in that direction. To take that step a little bit further, we want to remove the one step of backpropagation we have in this method. So what we do then is we remove the convolution before the sim loss, and we need the linear layer before the cross entropy loss, but we train it using with feedback alignment, which is you take a random projection of the gradient instead of using the transpose of the weight matrix. We also use random projections of the labels at each layer. And it hurts accuracy a little bit, but it still works surprisingly well. Yeah, so to summarize, we train each layer on its own without using global backprop. We use two loss functions, the standard cross entropy loss and a similarity matching loss, which is it's a squared error on similarity matrices. And this works surprisingly well on VGG-like networks. So before I take your questions to me, I'd like to sort of plant some questions into you. Because what we've done here is we've just barely prodded this space of local loss functions and almost immediately stumbled upon something that really helped quite a bit, at least in the setting of local learning. And that sort of opens the questions of what else is there in this space? It seems to be fairly unexplored. And there's some work on like neural architecture search and some work that's been done on learning loss functions with SGD. I think that's a very interesting area. It seems like there's a high likelihood of there being something else in this space that's not been found. Also, it's not really clear why this should work, since we're training like 11 layers that don't really know about each other. They know about the input from the layers below them. How is it that they're not discarding information that the layers above need? That's not really clear. I think very interesting to understand that much better. Also, it could be possible that something like this is happening in the brain. How would we find out? So, thank you. I'll take questions.
We do have time for questions. Please approach the microphones in the aisles.
I have a question. As I understand, your work is based on classification problem. Is there a way to extend your work to the regression problem?
It's a good question. We haven't tried that. I don't see any reason why it wouldn't work. Like, the question would be, so we have...
Is it a way to extend your architecture to the regression problem?
Right, so I would... We have two losses locally, which are like classification-based losses. So the question would be, if you substitute those with a regression loss, like a squared error, how would that work? And I would expect that it could work well. We haven't tried it, but the way to do it would just be to swap out those losses we use, because they need labeled. They are classification losses, but if you swap those out with regression losses, it might also work. Yeah.
Thank you.
Hi, so the VGG architecture is quite old, and like for most of the computer vision tasks, we use ResNet. For residual connections, it's not obvious to me how can you train the layers separately.
Right. No, the idea of these skip connections presumably is to help propagating the gradient backwards, which we don't need. So we have done some experiments with ResNets, and we find that it works better if you just remove these residual connections. Yeah.
So thanks for the nice work. It reminds me of a paper we presented at NeurIPS 2006 on including greedy layer-wise supervised training, where at each level we train each layer in a supervised way, and then we use a representation that's being learned as input to the next. And you have something that's smoother across all the layers at the same time. And one problem with this kind of approach that we found is that it's too greedy, right? The lower layers are never getting an incentive to learn representations that are particularly useful as part of a deep composition of many transformations, right? They don't get any signal that tells them that representation that they are looking for should be good not just immediately, but as a building block for something deeper. And that turned out to lead to suboptimal results compared to pure backprop supervised learning, at least in the experiments we run. So have you thought about this issue?
I've thought about the issue, and it's not clear to me if this network solves that issue, or if...
How could it? There's no signal to learn that what each level is doing is going to be a building block for downstream layers, right?
Exactly. And my expectation going into this was that that would be a big problem, and that's why this wouldn't work. And empirically, it seems that it does work. So why that is the case is still a bit of a mystery to me.
It may depend on the kind of task you're trying to solve, right? So a task that can be solved fairly well with a somewhat shallow architecture might be okay, but one that requires much more nonlinearity might be more difficult, I would guess.
Yeah, absolutely. I think an interesting thing to work on is maybe perhaps explicitly try to maintain information in the layers so as to avoid that problem. Yeah, thanks.
Thank you, Lars. So our next talk is about graph Markov neural networks and will be presented by Jiang Tang.
Okay. Thanks for the introduction. I'm Jiang Tang from Mila. So the title of our paper is Graph Markov neural networks. So this joint work with Montreal and also Yoshua Benjo. Okay. So we started a very fundamental task on graph, which is a semi-supervised node classification. So given a graph G, so V is a set of nodes, and E is a set of edges. So XV is a node features. So given some label nodes, so we want to infer the labels of the rest of nodes on the graph. So this is our task definition. And this problem actually has been widely studied in the traditional statistical regression learning methods. So essentially, for these methods, we try to model the joint distributions of the node labels given the node features with conditional random fields. So basically, the joint distribution can be modeled in this way. So here, phi ij is a potential functions defined on the edges, so which is usually a linear combination of multiple feature functions. And zxv is a partition functions. Okay. So during learning, so we try to maximize the likelihood of the observed labels, and also during inference, we try to infer the posterior distributions of the node labels of the unlabeled nodes. Okay. So the advantage of such framework is that so we are trying to model the joint distributions of the node labels. In other words, so we are able to model the dependency between the node labels. But for the disadvantage, because usually we have to manually design some potential functions, and these potential functions are usually a linear composition of multiple feature functions. So in other words, the capacity of these models are very limited. Moreover, the inference precision are usually very difficult because the graph structures could be arbitrary. So in practice, so we usually have to use some approximation methods for the inference. So another type of methods for prediction on graph is recent very popular graph neural networks. So essential idea of graph neural network is that so we try to learn effective node repetitions by iteratively aggregating features from the neighbors. So once we have the node repetitions, we try to predict the label of each node independently. So such a method including like, for example, graph convolution networks, graph attention networks, or more in general, this can be summarized to the neural message passing frameworks, okay? So the advantage of graph neural networks is that so we are able to learn very effective node repetitions by multiple nonlinear feature propagation layers. So usually the capacity of the model is very high, okay? But for the disadvantage, because during the inference, we try to predict the label of each node independently. That means we ignore the dependence between the node labels. So in this paper, we propose a graph markup for neural networks, so which try to combine the advantage of the statistical regression learning and also graph neural networks. So we try to learn very effective node repetitions, but also we try to model the dependency between the node labels. So specifically, we model the joint distribution of the node labels YV conditioned on the node features XV using conditional random fields. And then we optimize this model using a pseudo-likelihood variational EM algorithms. So more specifically, so we have two kinds of graph neural network. So one graph neural network is a P5, so which is a learning network. So this network trying to model the distribution of the label of each node conditioned on the labels of all its neighbors, right? So essentially, with this graph neural networks, we try to model the label dependency through nonlinear label propagation. So this is a learning network, and then we have another network, QCETA, so which is the inference network. So this network tries to learn very effective node repetitions to predict the label of each node. Through nonlinear feature propagation. And then once we have these two graph neural networks, these two graph neural networks will collaborate and co-train with each other. So more specifically, during inference, we will label the unlabeled node with the inference network. And then once we have the fully labeled graph, so we can train the learning network P5. And based on the learning network P5, so we can predict the label of the unlabeled nodes, so which is kind of like served as pseudo labels. And then by combining the pseudo labels and also the label nodes, we can train the inference network. Okay. So we evaluate our models on a bunch of tasks, including the classical semi-supervised node classification, and also on supervised node repetition learning, and also link classification. So we achieve state performance on all these 3 tasks. And the codes of our model is available online. And if you want to get more details, welcome to our post at the number 7 tonight. Thanks very much.
Next talk is about self-attention graph pooling. It's going to be presented by Junior Lee.
Hi, I'm Junhan Lee, and this is Inyam Lee. We are going to talk about self-attention graph pooling. In recent years, deep learning for graphs has become an intensive research area due to its outstanding performance on graph structural data. All GNNs are flat architecture that is a simple stack of graph convolutional layers. Recently, however, GNNs have been gradually advanced to various architecture for each task and objective. For example, graph unit architecture for node classification and hierarchical architecture for graph classification and graph autoencoder for link prediction. There are 2 main components in GNN architecture, graph convolution and graph pooling. The graph convolution is a fundamental operation aggregating neighbor node features on graphs. The graph pooling, which is our interest, reduce representation size and produce hierarchical representation. The goal of our work is to develop efficient graph pooling method, basically for graph classification. We thought there are 2 conditions to build the efficient graph pooling module. At first, it should have low complexity. Secondly, it should consider both graph topology and node features. The key idea of our method is to utilize GNS for graph pooling. The details will be described later. Graph pooling methods are used to summarize the graph into a fixed size representation regardless of the number and the order of nodes. Unlike global pooling methods, the hierarchical global pooling methods are designed to get graph structure even after the pooling. Diffool learns differentiable soft assignment matrix, which is mapping all nodes into a set of clusters by using GNNs. Duple is one of the sparse graph pooling method which is operated by node selection, and it has lower computational complexity than Diffool.
Now I'm going to explain the mechanism behind self-attention graph pooling. First, the attention score is calculated through graph convolution layers. Based on the score, the top k number of nodes are selected. These nodes create a new adjacency matrix, and the score is multiplied to each feature vector, and the results become the feature vector leading to the next layer. One thing I want to emphasize is that you can use the graph convolution layer when calculating the attention score. For a fair comparison, we used the proposed model architecture of previous works and changed only the pooling method during our evaluation. The figure on the left shows the architecture used to compare global pooling method, and the figure on the right is for hierarchical pooling method. Of the graph benchmark datasets, we chose 5 datasets with the most amount of graphs. We applied the same early stopping criterion and hyperparameter selection strategy to all methods. We created 20 different splits for each dataset and conducted 10-fold cross-validation for each split. PyTorch geometric package was used for implementation. The first 3 lines show the results of global pooling methods, and the bottom 3 lines show the results of hierarchical pooling methods. It is clear that results have consistently improved. Note that results were achieved without compromising memory nor computation efficiency. Additional details and information will be discussed during the poster session. Thank you for listening.
In our next talk, Sunil Thunalasian is going to tell us about how to combat label noise in deep learning using abstention.
Thank you. So one of the practical challenges when you're trying to deploy a deep learning system is that state-of-the-art models all require large amounts of clean, annotated data. Consider ImageNet, for instance. This has been referred to as a data set that transformed AI research. And what was the effort? 49,000 workers, 167 countries, almost 3 years to finish. When you're dealing with data at scale, a couple of approaches are there. You can crowdsource it, labor-intensive but cheap, or to speed up the process, one can use weak labels from queries, user-defined tags, and so on. This is fast, but most of these approaches lead to significant labeling errors. And some amount of labeling error is OK, but if the label noise becomes large, then the performance of your classifier can degrade quite significantly. So when you think about label noise, it's really an inconsistent mapping from features to labels. And in that sense, it should make training hard. In this work, we introduced the deep abstaining classifier. And the idea is this. We use the learning difficulty while training to abstain on classifying while continuing to learn on the non-abstain samples. And then finally, only classifying when a consistent feature mapping has been learned from features to labels. So how do you train a deep abstaining classifier? You start out with a regular cross-entropy or K classes for a K-class classifier. And then you add an extra abstention class at the loss layer. And the idea is that the deep network can put mass in this abstention class and can punt. It can reduce the cross-entropy of the error that it's making on the true classes. But if you only do this, then it's going to punt all the time. So to penalize abstention, we introduce an extra term. So the idea is that the deep network eventually learns on the true classes while having this abstention option. So the dynamics are like this. If you, after an initial warm-up period, you introduce abstention, and then it abstains on most of the things except just the easy stuff. And then as it learns on the easy stuff, abstention reduces, and finally it abstains only the most confusing samples. And it turns out that in the presence of label noise, it's these samples that it abstains on towards the end of the training that are most likely the noisily labeled data. And if we train like this, first we use the deep abstaining classifier to identify label noise, clean the set, and then train on a cleaner set, we can get state-of-the-art results in many label noise experiments, including a real-world noisy data set, which is twice the size of ImageNet, 1,000 classes, and does not have any human annotations in the training set. There is another interesting aspect of the abstaining classifier. Because abstention is used during training, if there is systematic label noise in the data, that is, if there is a pattern to the label noise, then the abstaining classifier precisely picks up these patterns and abstains on it during testing. For example, in this experiment, in the random monkeys, we take the STL10 data set and randomize all the images, all the labels on the monkey set. And what happens is, during testing, when presented with monkey images, it abstains with remarkable precision on all the monkey images in the test set. So it's learned a representation of monkeys, but because of label noise and the way the loss function is constructed, the feature mapping from monkeys now is directed towards the abstention class. You can do a similar experiment with image blurring. You blur images in the training set, and the idea is you randomize the labels on this blurred images, because blurring images makes the data hard to label. And then when presented with blurry images in the test set, it abstains on nearly all of them. And at the same time, it also maintains high accuracy on the non-abstained results on the non-abstained set compared to the baseline DNA. So in conclusion, abstention training we've seen is a very effective way to identify and clean label noise, but it also can be used to learn representations for label noise, and that's very useful when you have to interpret the decision of an I don't know classifier. The code is available at GitHub. I'd like to thank my co-authors, and we will be at Poster 9 tonight, so hope to see you there. Thank you.
So the last talk of this session, Huayu Li is going to tell us how to learn to generate matching networks for future learning.
Hello everyone, I'm Huayu Li from Cassia. I'm going to present our work learning to generate matching networks for few-shot learning. We know that deep neural networks are trainable and powerful. If we train a network with SGD algorithm from scratch, it overfits when training data is scarce, and it fits well when training data is sufficient. The weight determines the the functionality of neural networks. So we can regard the functional weights as a conditional distribution over training data. In order to directly obtain the functional weights of a neural network for a few-shot learning task, we propose to learn a neural network to directly generate weight for another neural network just from a few training samples. This is the architecture of our approach for few-shot learning, a 5-way one-shot few-shot learning task. It contains 2 key components. The target net module is a neural network with fixed architecture designed for classification, and the meta-net module aims at encoding training samples and generating functional weights for the target net. For high-dimensional inputs, we use an embedding neural network to extract low-dimensional features. In detail, the MetaNet module consists of 2 parts. The task context encoder represents all training samples to produce a fixed-size task context feature, and the weight generator is to produce the weight of the target net based on the task context feature. We also apply the weight normalization on the generated weight to constrain the scale out, and it facilitates the training. The target net module, we use the matching networks as the computing structure, and the weights of each layer are generated by the MetaNet. We summarize the learning algorithm in this algorithm. We also use the few-shot task episodic training procedure. From the meta training dataset, we can sample task batches. And for each task in a task batch, we can sample functional weight for the target net from MetaNet using training samples. And we accumulate the loss in a task batch. Intertask normalization strategy is proposed to incorporate information across tasks in a task batch. And finally, we update the parameters in the MetaNet. When comparing with other meta-learning approaches, the learned prior knowledge is represented in different forms, such as good initialization, optimizer, mapping function, or others. Our approach represents prior knowledge in a conditional weight generator. The advantages are for unseen tasks, the neural weights are dynamically adapted, and further fine-tuning is not necessary. We conduct a synthetic dataset experiment to show our intuition. When comparing, we compare the decision boundary of the target net with different weights. We can see that the target net with generated weights show clear, better decision boundary than the directly trained weights. This is because the weight generated by MetaNet contains prior knowledge for solving similar tasks. We also evaluate the effectiveness of our approach. We achieve competitive performance on a manipulated dataset and state-of-art one-shot learning performance on mini-net. We do evaluation study and show task context encoder and inter-task normalization contributes a lot. Thanks. More details will be at poster.
So this concludes the session. We have a lunch break, and the afternoon session starts at 2 p.m. See you.